So we've been seeing questions where we have to find the initial rates of reactions. Using the initial rates of reaction or initial concentrations, we've got to find the rate equation. But what you've noticed in the questions that we've done so far, you notice that all of the questions there are experiments where one concentration of a reactant remains constant and the other reactant's concentration changes, and then vice versa. But sometimes that doesn't happen in the real world. For example, let's look at what I'm saying is exemplified by this question. In this case, an experiment is carried out between E and F, two reactants. And the initial concentrations for 3 experiments are given for E, and the initial rate is given for all the 3 experiments. And the reason why this is not as straightforward as the others is because there are experiments where E is constant and you can use those to find F. But there is no experiment where you can keep F constant, or where F has been kept constant to find the value for E. You notice that? So this becomes not so straightforward. So what you do is you first find that fellow where the other guy is kept constant. So now I notice that in experiments 2 and 3, E is kept constant. E is right here, and right here. So in experiments 2 and 3, E is kept constant. And F is changing by a factor of what? In experiments 2 and 3. By a factor of 1.5. Yeah? And what is rate changing by? The rate isn't changing at all. You could say it's a factor of 1, but it's effectively saying that you changed the concentration of F, but there was no change in rate. What does that tell you about the order of F? So the individual orders for F, where F in experiments 2 and 3 is increasing its concentration, but the rate is not changing. That implies that the reaction is 0 order with respect to F. What that means is, regardless of whatever you do with F, will have no impact on the rate of reaction. Yeah? Once you figure that out, what that means is, now you don't have to worry about F, because F is 0 order. So you have to have no worries of F. That means now that if I compare experiments 1 and 2, and why am I going to compare 1 and 2? Because that's where E is changing. Either it's 1 and 2 or 1 and 3. It doesn't really matter. If you compare 1 and 2 or 1 and 3, you'll see it won't matter. Because F is, though changing, it has no effect on rate. What that tells me is that the only thing that's going to affect rate in 1 and 2 is doubling E. And if I double E and the rate doubled, that's a first order relationship. And we can only make this claim because we've discovered that F is 0 order. So if F is 0 order, and if I double E and the rate doubles, what is that in terms of order for E? That implies that the rate is directly proportional to the concentration of E. We've already decided that rate is independent of F, which F is 0 order. But because of that, all the change in rate in 1 and 2 came because of E. And E doubled, rate doubled. It's first order. You could have also compared 1 and 3. And if you compare 1 and 3, E is doubling, F is tripling, but the rate is only doubling, which means it was also because of E doubling. So here E is first order, F is 0 order, overall order is 1, and the overall rate equation is K into E. That's it. No F in here. And how would I find the value for K and the unit? Plug in any experimental data. Take equation number 1. You'll get this in this. And K will come out to be 0.4. And since this is moles per dm cube and this is moles per dm cube per second and moles per dm cube, K in this case will only be per second. So K is 0.4 per second in this question. Now let's take a look at even more trickier fun questions from deducing rate from initial from rate equations from initial concentration and rate equations, rate data. So here I've got a table. When an experiment is conducted between P and Q, those are your reactants, P and Q. And it's saying deduce the orders with respect to P and Q. And you have initial concentration and rate. And you might think it's pretty straightforward. There's a small issue. Because there are experiments where Q is constant and you can find the order with respect to P. But there's no experiment where P is constant and you can find Q. But let's do it in steps. Well, easily speaking, I can easily find out with the order with respect to P if I take experiments 1 and 2. Why? Because in those experiments, P is tripling, P is changing by a factor of 3, and Q is not changing. And when I look at the rate, it is changing by a factor of how much? By a factor of 3.
Quick pause. If you're finding value in this explanation, there's so much more to discover at Alt Academy, where we break down every A-level concept with the same clarity. Now back to the video lesson.
What does that tell me? That if P triples, the rate triples. What does that tell me? That tells me that P is first order. So the rate is directly proportional to P so far. What that means is, in any experiment, if I double P, the rate doubles. Understand what first order means? It means that if I double P, rate doubles. Just because of P. If I triple P, rate triples. If I quadruple P, rate would quadruple. That's what first order means. Because we will now use this relationship to find out Q. So now to focus on Q's effect on rate, what I would do is I would take any experiment, because where Q is changing, either I can take 1 and 3. I'll take 1 and 3, just simple. Why is 1 and 3 simple? Because 1 and 3 and 2 and 3 both have the same effect on Q. But in 1 and 3, it's very straightforward what's happening to P. P is changing by a factor of 4. And Q is changing by a factor of 2. Yeah. And what is the rate changing by? Look at that. P is quadrupling, A is doubling. But at this stage, we already know P is first order. So basically, if P is first order, by quadrupling P, the rate should quadruple just because of P. But if I look at rate from 1 and 3, the rate is actually increasing by a factor of 16, which really is 4 times 4 is 16. And why would I do 4 times 4? Because P, which is first order, should have increased the rate only by a factor of 4. But this increased by a factor of 16. So breaking it up means that this is really 4 into 4. Why 4 into 4? Because the first 4 is what the effect of P was. That P was quadrupling and it's first order, so the rate should have quadrupled. But the rate quadrupled, really. Which means that the second 4 is because of Q doubling. But if Q doubles and the rate quadruples, what does that tell me about the relationship of Q and rate? It tells me that rate is proportional to the square of Q, which is, therefore, Q is second order. Now, if Q was 0 order, P quadrupled in 1 and 3, the rate should have only quadrupled. If P was first order, quadrupling P and doubling Q should only increase the factor by 8, times 4 because of P, times 2 because of Q. Because Q is second order, it was times 4 because of P is times 4, and 2 squared because of Q doubling. And that's how you can deduce, even if you don't have P constant for Q, because you already found the order with respect to P. And using that, you find the order with respect to Q. Let's take a look at another such example where you don't have constant concentrations. This is a reaction between a haloalkane, let's call it RCl, with a OH. And there were 3 experiments. In all 3, RCl was changed and OH was not changed in 2, but changed in the first one. So just to find the order for the haloalkane, all I had to do was take experiments 1 and 3. In 1 and 3, OH is constant. Do you see that? OH is constant. but the haloalkane increased by a factor of 3, and the rate also increased by a factor of almost 3. Approximate because experimental data hai. So the concentration tripled, the rate tripled, therefore at least the haloalkane's order is first order. That I have found. That part is easy. Now I want to find the order with respect to the OH. The problem is there's no experiment where OH is changing and haloalkane is remaining constant. But I know OH is changing between 1 and 2. So if I take 1 and 2, I notice that OH is doubling and the haloalkane is doubling, right? But we already know the haloalkane is first order. And the rate should double just because of this guy, shouldn't it? And whatever else happens is because of this fellow. But if this is first order and if the concentration doubled, the rate should double just because of this fellow. And then if whatever this is order, that also affects rate. But when I actually look at rate for the first two experiments, it just seems it's only doubling. So it's only doubling, and I knew that fellow is first order haloalkane, and that's doubling. That means that OH doubling really had no effect on rate because this was only double. So if OH has really no effect on rate, what order therefore is OH? Therefore OH is 0 order. So here the rate equation was simply R equals to K into the haloalkane and not OH. Alright?
Hey there! If you found this A-level chemistry lesson helpful, why don't you head over to our website altacademy.org, where you can sign up for the full A-level chemistry course. In addition to chemistry, you can sign up for physics, biology, math, or 4 other A-level subjects. Thousands of students have already taken the leap. What are you waiting for?